In this video, we're going to look at the 3D divergence theorem, probably one of the most useful theorems when it comes to vector fields. We're going to define a closed surface, and we'll say that a closed surface bounds a solid region. So let's do just some visual examples of what a closed surface might look like. If you had, say, a sphere, that's an example of a closed surface because you're trapping points in 3D inside that surface. Similarly, you could take, say, a cube. So that cube bounds a solid region in 3D. So let's say those are closed surfaces. An example of a surface that's not closed, let's say a paraboloid, for example. So this paraboloid is an infinite surface. And imagine you had, say, a particle sitting here. There would be nothing stopping this from just flying out here. So that paraboloid does not bound a solid region, therefore it's not a closed surface. So now we can jump into the 3D divergence theorem. The setup is that we have a closed surface, S, that bounds a solid region, Q. And here's the statement of our 3D divergence theorem. So we're going to be looking at the flux of the vector field F across our surface S. To indicate that that's a closed surface, you'll sometimes see a circle on the double integral like that. We'll talk more about that in a moment. And the divergence theorem says that to compute this flux, what you can do is do a triple integral over the solid region Q. What you'd be integrating the divergence of F. So let's look at this double integral more closely here. That's called a closed surface integral. That's what the circle on the double integral indicates. And that's just a way of emphasizing that our surface S is a closed surface. So it's not wrong if you didn't have the circle on there, it's just for emphasis. So let's see if we can put this 3D divergence theorem into words. If we look at the left side here, this is the flux. And we know that for closed surfaces, by default, the flux is considered to be outward unless otherwise specified. So let's say this is the outward flux of vector field F across a surface S. Might be good to emphasize that we use 3D divergence theorem just for closed surfaces. So let's say across a closed surface S is the triple integral of the divergence of F. So that's what our divergence theorem is saying in 3D. Before we jump into an example, let's just compare this to the 2D divergence theorem that we saw earlier. Line integral around a closed curve C of f dot n d little s is equal to the double integral over region R, divergence of f dA. So that applied in 2D if we had some curve in the xy plane had to be a closed curve. We're talking about the flux of our vector field F across that closed curve. And we said, well, we can rephrase that as the double integral over this enclosed region R here of the divergence of F. So if I now write down our 3D divergence theorem underneath that, now we're doing a double integral over a surface. It's a closed surface, so we put that circle on the double integral like that. We're still computing the flux, but because we're talking about a surface now, instead of writing d little s, we write d capital S. So for 2D divergence theorem, we're talking 2D flux. For 3D divergence theorem, we're talking 3D flux. It's still the integral of the divergence of F, but now we're integrating over three-dimensional regions. So we write dV instead of dA, and we just call our solid region Q. So if you wanted a picture to go with this, I would say maybe a standard picture to draw would be something like a sphere, just because it's an easy closed surface to draw. So there's our closed surface, and then the region that's trapped inside that surface is Q. So that's that solid region there. That's what you're doing your triple integral over. So let's compute the flux of this vector field here across a certain surface. It's going to be bounded by the following four surfaces. We'll draw a picture of that in a moment. And we say that the flux is outward by default for a closed surface. So this word outward here, I would say it's just for emphasis. Let's start by drawing a picture of our surface S just so we can visualize that. So looking at the first two surfaces, let's think about what's happening in the XZ plane here first. So one of our surfaces is Z equals 0, which is the XY plane. And the other one is this parabolic cylinder. Well, in the XZ plane, that's just going to look like a parabola. So it's got a z-intercept of 9, x-intercepts of plus or minus 3. So there's our parabola there. And because this formula here does not have a y in it, we've got a copy of that parabola at every y value. And then that parabola is being cut off at z equals 0, which is the xy plane. So that takes care of those two surfaces. And then we've got some boundaries for y. Y is going to range just between 1 and 4. So let's indicate some scale in the y direction. So let's say that's y equal 4. There's y equal 1. So I'm going to draw a copy of our parabola at y equal 1. Okay, and then we'll just connect some of these dots here. So this surface is actually formed out of 4 different surfaces. Let's just highlight them in our picture. So we've got z equals 0, which is our xy plane. So we'll draw that in blue there. That's z equals 0. We've got, let's say, the top part of this surface, which I might draw in red, formed by the parabola z equal 9 minus x squared. So that's a parabolic cylinder. So we let our y values vary. And then we've got the left and right surfaces, the y equal 4 and the y equal 1, like that. And we want to compute the flux of F across S, so that's the outward flux of our vector field across S. So what we want here is the total flux across all 4 sides of this surface, which we've got highlighted in our picture here. So it'd be quite annoying to compute the flux separately for each of those 4 bounding surfaces and then sum them up. The divergence theorem gives us a much faster way of finding the total flux across all the sides, all at once in one calculation. So let's start by calculating the divergence of F. So we're going to take the partial with respect to x of our first component, plus the partial with respect to y of the second component, plus the partial with respect to z of the third component. So that's going to give us 2y plus another 2y plus 0. So in other words, divergence of our vector field 4y. All right, then we need a description of the solid region Q that we're integrating over. So this is what's going to give us our limits of integration for our triple integral. So that's where a picture would come in handy. Let's think about slicing in the z direction first. So I'll just draw a big slice in the z direction here. So it'd be going from z equals 0, which is the xy plane at the bottom, and then be going up to our parabolic cylinder, which we could have labeled that. That was z equal 9 minus x squared. And then let's think about what's going on in the xy plane. So I'll draw a second picture underneath here, just in the xy plane. If we imagine projecting this surface onto the xy plane, just say shining a flashlight straight down here, figuring out where the shadow would fall in the xy plane, you might be able to see it geometrically. The y values would range from 1 to 4, and the x values would range from -3 to 3. So you'd just be getting this kind of rectangle in the xy plane. Let's record those limits of integration. Y would be ranging from 1 to 4, and x would be ranging from -3 to 3. And now we're ready to write down the divergence theorem. So what we're looking for, total flux outwards across our surface. So we'll just call that capital Phi. And according to the divergence theorem, we are going to integrate over that solid region Q, integrating divergence of F times dv. All right, so let's plug everything in. We've already calculated our divergence of f. We said it was 4y. We set up our dv by thinking about z first, then y, then x. So we should write dz, dy, dx, and then we'll put our limits of integration on there. So z going from 0 to 9 minus x squared, y going from 1 to 4, and x going from negative 3 to 3. Great, so let's work through the details of this triple integration. So keep our first two integrals on there, keep our dy dx on there, and then just integrate with respect to z. We'd have 4y times z, and then that z is going to get evaluated at 9 minus x squared, and z equals 0. Okay, so if we actually do that evaluation right in this step here, that would give us 4y times 9 minus x squared after that evaluation is done. So then we're ready to integrate with respect to y. Keep our outside differential on there. Integrating with respect to y, we'd have 2y squared times 9 minus x squared, and that's going to get evaluated at y equal 4 and y equal 1. All right, so we've still got our integral from negative 3 to 3 on here, and let's evaluate. So plugging in here, we'd have 32 times 9 minus x squared minus 2 times 9 minus x squared. Or if you did that a little bit more quickly, you could just keep that 9 minus x squared factored, and you could say that's 30 times 9 minus x squared. So let's do that. You could just keep that factored and then evaluate the 2y squared at the 4 and the 1. So 30 times 9 minus x squared, and let's just finish this off now. So integrating our 9 minus x squared, we'd have 9x minus x cubed over 3, and that's going to get evaluated at 3 and negative 3. So we get 30 times, well, subbing in x equal 3 here, we get 18. And then we're going to be subtracting off the value at negative 3, which is going to be another negative 18. Okay, so altogether, we're getting 30 times 36, which is going to give us 1080. So let's just do a quick recap of the context here and make sure we understand how useful this 3D divergence theorem can be. So the surface that we had described in the question here was actually formed out of 4 separate surfaces. And what we wanted was to calculate the flux of our vector field outward across that surface. So rather than having to calculate the flux across each of the individual 4 sides and then summing those up, we were able to just compute the divergence of f and do one single triple integral over the enclosed region. So if you want a little bit more conceptual understanding about why this 3D divergence theorem is true, I would recommend that you just look back at the previous video on 2D divergence theorem and 2D flux, where we did a geometric interpretation of why that theorem would be true, and the 3D divergence theorem is reasoned in a very similar way. Thanks for watching.